All right, welcome to the 7th session of the relation of the science of physics to theology. We're moving along here, only 3 more times after this one. So let's begin with a word of prayer. Gracious Lord, how great you are, how wonderful and magnificent is your creation. We thank you that you're allowing us to learn more about it, to understand its mysteries, and so to understand more of your magnificent power. We thank you for this in Jesus' name. Amen. A verse from Psalms. How great are your works, O Lord! Your thoughts are very deep. This time we're going to get into some of the deeper thoughts, some of the things that are not intuitive by any imagination. Quantum mechanics. It explains many things that classical mechanics cannot explain, and it leads us to some rather strange things, these things called uncertainty relations and statistical predictions. And these have some pretty deep philosophical implications to them. So I'll try to do a little explaining of this as we go along. Just as a quick review, we remember that God's creation is knowable and stable. His revelations are true, unchanging, and non-contradictory. We found that classical mechanics and thermodynamics led to these rules that we call conservation of energy and increase of entropy. And these rules remain valid even in those cases where the classical laws of motion are no longer valid. The laws of classical physics fail at extremes of size and motion. And it's those extremes we're now going to look at. Last week we talked about light. It's an electromagnetic wave. White light combines waves of many frequencies, and white light comes from white hot bodies, as you might expect from the name. Now we are going to see where we get into trouble trying to understand this, because the spectrum, and by the spectrum I mean the distribution of the energy in light into the different frequencies. The spectrum from what we call black body radiation, that's radiation from a hot thing that's heated up. So it may start out black, but then it gets red, and then it gets white hot, and it gives off the radiation like we get from the sun. We want to try to explain where that comes from, and using the concepts of classical physics, that is Newton's laws, the laws of thermodynamics, and the laws of electrodynamics, Maxwell's equations. We try to understand that, and it doesn't work. There's a problem. A man named Max Planck was first able to solve this mystery. He came up with a formula that explained it from first principles by making an assumption. And the assumption was that light doesn't come out in continuous form, but it comes out in only integer multiples of a very small amount, which is the letter H times the letter F, which stands for H is Planck's constant after him, and F is the frequency of the light wave. The product of those two is the amount of energy in a single unit that has to be there to explain this spectrum, okay? That if light is emitted in these little units of energy, then you can explain the way it actually is. Well, this H has a real fundamental place in a lot of things, as we'll see. It's called Planck's constant, and it's very, very small. When you see that 10 to the minus 34 in an exponent, that you put down the decimal point and then 34 zeros before you write the 662. So it's a very small number, okay? And Joule second, that's just a measure of, Joule is an energy measurement in the metric system, and second is the time unit that we know about. So there is a lot here, and I'm not going to be able to tell it all in 1 hour. So I have a long reference, which is very, very long and you wouldn't want to type all that in. So I will email out a link that has that in it in case you would want to go there. But it's quite interesting. There's been a little rebellion in the scientific world against the high cost of textbooks. When I retired from K-State, and that's been over 10 years ago now, the price of a textbook for one of my courses was over $100. And I thought that was ridiculous. And there's been quite a bit of inflation since then. Well, there's been a little bit of a rebellion, and there are people that are working to provide free textbooks. And here is one. It's from the University of California at Davis, and it's at the website libretext.org. And you can find there textbooks on lots of topics. And in particular, you can find a discussion of what we're going to be talking about today, optics and modern physics and quantum mechanics. And if you go there, sort of play around with that, you could get a college education reading that website. There's some others that are doing the same thing. I think MIT has also put some of their courses online. So there are a lot of places now, if one's really curious, that you can investigate these things sort of as a hobby without having to pay, all right? And for the student in the subject, if a professor adopts one of these online books, saves them $100 or $200, whatever. Book publishers don't like that, but that's another story. Okay, here we have a graph. We've had a lot of graphs in here, but this one is showing the distribution of the energy in white light that comes off of a hot body, like an incandescent light bulb or the sun. And what we find is there's some peak value, and then it goes down away from that in both directions. And this scale along the horizontal is the wavelength, which means the frequency is higher where you get to the shorter wavelengths, and the frequency is lower to the longer wavelengths. And this is again in this nanometers that we talked about last time, 10 to the minus 9 meters. So anyhow, the visible light is sort of in this range. And then we have the longer wavelengths with the infrared, and finally, very, very low wavelengths. And then going the other way, we get the ultraviolet. Well, in attempting to explain this theoretically, Raleigh and Jeans, two different scientists together, had a theory based on classical physics, which predicted this blue line, which doesn't come anywhere close to the actual one, because the actual one is essentially what Planck got. I don't have on here the experimental data, but if you were to draw a curve and show experimental data for the observations, it's right on top of Planck's curve, which is the reddish one. And I'm not sure you can even tell that at a distance which one's red, but the red one is the one that's the upper of these two right here. And then there's another theory by Wien, which gives a curve that's very close to Planck's curve, but not quite. And in particular, when you move out to the longer wavelengths, they don't agree. So here we look at the much longer wavelengths, and now we see how we have three curves, and that Planck's is different than the other two. Well, at any rate, his is the one that fits with the experimental data, and it requires that light be emitted in these little packages, which are called quanta for, quantifying things. They call them quanta, and they have the value of HF, which is a small number. Okay, well, that was one place where light didn't seem to agree with classical understanding of physics. Now there's another one called the photoelectric effect. The photoelectric effect I will have to explain a little bit, because if you don't know what that is, if you were to take a situation like a container like made out of glass so you can let light go through it, and you put a metal plate on this end and connect out through it, and a metal plate on this end and connect out through it, and you put a battery out here, and that battery is going to provide an electrical voltage between the plates, and then you shine light on one of them. Well, what's going to happen? Well, the light will cause electrons to be knocked loose from this piece of metal, and they'll fly across there, And not if you connect it that way. I've got to change the polarity of my battery to make the electrons go this way. And the electrons will fly across there and you get a current, and you could actually measure the current on a meter. And that's the photoelectric effect because light is producing the current. Now, classically, you would expect that the frequency of the light that you get out, or the frequency of the light would have some effect on the current. The intensity of the light would have some effect on the current, but the effects are not what you observe. What you observe are rather strange, and it's something like this, that if the light has too long a wavelength, too low a frequency, you don't get any electrons at all, no matter how bright it is. And if it's above that, then the amount that you get is dependent again on not just the frequency, but on how much light you're shining on it, which you'd expect. Well, where does this all get explained? Well, it gets explained by saying that the only way you can understand this is if this stream of light is a bunch of little particles, each one having this energy, HF, as the energy of the individual particles, energy, okay? If that's high enough, it can knock an electron out. If it's too low, it can't. So that's why the frequency has to be sufficiently high or you don't get any current out of it at all. And so Einstein has now gone back to Newton. Newton said, well, light is a stream of particles coming. And then there was another man back in Newton's day named Huygens who said, no, light is a wave motion. Well, last week we talked about light as a wave, an electromagnetic wave, and that's pretty well understood to be the truth. And I'm going to show you an experiment here in a little bit that will show that light is a wave. But Einstein is now showing, it can't be a wave, it has to be a stream of particles or we don't get the photoelectric effect. And the other way around, the black body radiation said it was coming out in little bits of energy, so that agrees with being a bunch of particles. So what's going on here? Is it particles or is it waves? Well, it's both. Light is an electromagnetic wave, and you can show that by a little experiment that we'll do here in a minute. So how do we explain it being waves and particles both? Well, it's called the principle of complementarity, where we say the amplitude of the wave gives the probability that the little particle is there. So the higher the amplitude of the wave, the more little particles will be there. And the lower the amplitude of the wave, the fewer particles will be there. Okay, so that's kind of strange. Well, it gets stranger. Here's an experiment. Have a thing called a diffraction grating. And you put a beam of light through it, and it splits into two directions. Now, how does that prove its waves? Well, let me give you another example up here. Okay. Suppose I have a bunch of slits in a wall, like that. And I were to throw a bunch of little particles at it, who knows, maybe pollen grains, something that I'm going straight like that. That would correspond to light as a stream of particles, and the stream of particles would hit this, and the ones that hit here would get absorbed or bounce back or something, and the ones that didn't would just go straight on through. So what we expect to see on the other side would be it coming straight on through, but maybe a little less intense. That's if it's a stream of particles. But what if instead of a stream of particles, what we had out here was waves? Now to redraw this thing, it's the same wall with the same holes in it. And now we have these waves, which we kind of represent like this. Remember the waves on the surface of the ocean or on the pond or in your little fish pond? And when they come here, when they get here, at each one of these places, they go through and they start to come out like this. Each little opening like starts out a new set of waves. and they overlap each other, and they cause what's called interference. Some places one's going up and the other's going down, and they cancel out. Some places they're both going up and they get bigger. And the result is, what you find is, when you get far enough away, there's now a wave going out like this, and down here there's another wave going like this, and there's still one going straight through. And you can get a mathematical relation between the wavelength, that is the space between the places where the waves are high, and the spacing here on this screen, and the angle at which they go out. So there's a mathematical relationship between those. Okay. Well, now I'm going to actually do it for you, because I brought along today a laser. Woo! See a little red spot? Okay. I also brought along a thing called a diffraction grating. And what this is, it looks like a 35 millimeter slide. If you look at it, it looks like it's plain. There's nothing there. There are actually 1,000 vertical lines in every inch. Woo, 1,000 lines. That's what it says on it. Sorry, 1,000 lines per millimeter, not 1,000 lines per inch, 1,000 lines per millimeter. That's why I can't see them. It's very small. Well, at 1,000 lines per millimeter, I wonder what in the world will happen. It's like my wave going through there, or is it going to be like a bunch of particles going through there? In other words, when this laser beam hits it, will there only be one spot, or will there be three? So here's the laser beam. You see around me? And now here it is with this. The other spots are out there if you can see them. They're not very bright. See the left and the right at the right edges of the board? Okay. I'll get closer. Now you can see. All right. Now, if I was not so shaky and we held that real still, and we measured the angles out there, and we measured the distance there, and we knew that was 1,000 lines per meter, then I could find out what was the wavelength of this laser. But it tells me that the wavelength of this laser is 560 nanometers. So knowing that, and measuring all those things, I could tell you how many lines per inch were on here. Those two are interrelated. At any rate, I've just proven to you that light is a wave, okay? Not particles, it was a wave. Einstein just proved to you it's particles. How are we going to have both true at the same time? It's this idea that the wave motion guides the particles. And where the wave is bigger, there are more of them. Where the wave is smaller, there are less of them. Okay, and we will go on then and see how that idea goes farther. Okay, now, maybe you remember from chemistry or physics, the Bohr model of the atom. Remember the idea of atoms? Atoms, the smallest thing you can get and still have a substance. And for many, many centuries, the idea was you can't split an atom. It's the smallest thing there is. Well, in the 20th century, we begin to figure out that the atom isn't just a little round billiard ball. It has a structure. And the idea of the structure is it has what's called a nucleus, and the nucleus contains all the positive charges, the protons. And it also contains other particles that have no charge called neutrons. The number of protons is called its atomic number, and the simplest one is hydrogen, which has one proton. And then the number of both protons and neutrons together is called the atomic weight, which for hydrogen is 1 again. But for helium, it's, what is it for helium? Helium, it depends on which isotope you have. Helium-4, 2 protons and 2 neutrons, that's the ordinary helium. But at any rate, you've got all this positive charge in the nucleus, but the atom is neutral because there are electrons around it. Around it here are electrons. And how are they around it? Well, the Bohr model says they go in circles. So we have the nucleus here, and the electrons go about it in circular orbits. It's back to Copernicus again. Circles around the center. And by the way, as an aside, maybe Bohr didn't take that seriously, but he used it for his mathematical model. At any rate, the idea then is you have as many electrons as you have protons, but if you had just one electron, like a hydrogen atom, one proton and one electron, that one electron could be in various orbits at various distances away from the proton. And you can calculate an energy associated with them because of this circular motion of saying how much energy they would have. And when an electron moves from one orbit to another, the energy that it gives up comes out as one of these HF photons. That's a coined word now. Heard of photon? It's the little packet of energy in light. And that amount of energy determines the wavelength of the light. Well, this is observed in spectroscopy in that if you have hydrogen and run an electric current through it and heat it, the light that comes out of the hydrogen is not white. It's not a mixture of frequencies. It's single frequencies, but there are more than one of them. There are separate spectral lines, as they're called, and they're at different frequencies. And when you know the different frequencies, you can therefore say, what's the spacing of these electron orbits? Now, Bohr was quite successful in predicting the spectrum, not only of hydrogen, but also of other atoms. And there's a whole theory worked out on this. It's called the old quantum mechanics. And it contradicts classical physics in the following way. Theoretically, if you have an electron moving in a circle, it's going to radiate electromagnetic waves out of it at the same frequency as the frequency of its rotation. This is called cyclotron radiation, and it can be seen in this big machine called a cyclotron where the electrons are going around very fast, and so it radiates energy. I could see it in an experiment I worked on back at Oak Ridge, which is called Elmo Bumpy Torus, and it was heating a plasma by using electromagnetic waves, and it produces electrons that were in very tight, fast little orbits, and they radiated a lot of energy. In fact, they told us that where this machine was, it was behind a big lead wall, that if you went in there when it was running, there was enough radiation to kill a horse in a minute, whatever that means, okay? So you get a lot of energy that way out. Well, what does that mean? Well, it means that these orbits couldn't be stable because they would radiate energy away. They would spiral in, and in a very, very short amount of time, they'd all be on top of the nucleus. But Bohr's model has to say that does not happen. So that's a place where it contradicts the classical physics understanding. Now, Bohr's model explains the spectrum all right, and it's successful, but it doesn't explain everything. There's another theory that comes along then. De Broglie hypothesized that electrons are wave motion, just like light is wave motion, or that there's this duality between an electron wave and an electron particle, like there is between the photon and the light wave. And you can actually then show how Bohr's orbits will work out in terms of waves, if you like. The next step, a man named Schrodinger comes along and develops what's called wave mechanics, which gives a mathematical method to find these waves associated with electrons or other particles and how they would be guided and develop over time. Okay, well, here's the picture kind of showing the idea of how you would make Bohr's orbits out of waves. The smallest orbit is just a circle, which is a wave of essentially a zero frequency, if you like. And then the next one is the wavelength going around is you get 2 ups and downs of the wave going around. And then the next one is you get 3, and so they give levels 1, 2, and 3, and so on. And it just happens to correspond to the levels that you observe with the spectroscopy of the hydrogen atom. So the wave mechanics explains it, and, well, it's all the explanation we need, right? Well, yes and no. What we do find is you can do another experiment, like the diffractions experiment with electrons, and you find out the electron beam splits up and goes out just like it was light waves. Ooh, okay. So now life is getting confusing. Are electrons waves, or are they particles? Are anything else waves or particles? And for that matter, if you took a bowling ball, which is pretty massive, and considered it as a big particle, and tried to use the same ideas that Schrodinger does for the electron, you would find out that the formulas work okay, but the wavelength is extremely tiny. So tiny it could never be observed. And so therefore, for massive objects, the new quantum mechanics, as it's called, agrees with classical mechanics. There's no conflict there. It's just when things get very, very tiny that you begin to notice these wave effects. Well, one of the consequences of the wave description of electrons is that you can't know where it is and how fast it's going at the same time exactly. There's always an uncertainty in your understanding, and the uncertainty is related back to Planck's constant again. The uncertainty in your knowledge of the momentum, that is the mass times the velocity, and your uncertainty in the knowledge of the position, where it is, the product of those two uncertainties is always greater than or equal to Planck's constant divided by 4 pi. And the Planck's constant over 4 pi turns out to be more fundamental than Planck's constant, but that's another story. Okay? So that's known as Heisenberg's uncertainty principle. Maybe you've heard of that before. Well, that uncertainty principle can be generalized, and we'll talk about that in a little bit. But first off, let me say that now there's a more abstract formulation of quantum mechanics, the explanation of how everything behaves in the universe, if you like, at the small scale. And this more abstract form includes Schrodinger's wave mechanics as just one way of expressing it. And there are other ways you can express it, like using a mathematical form called a matrix, and so on. This quantum mechanics reproduces Newton's laws as long as you have objects with masses bigger than molecules. This is called the correspondence principle. It means that the new theories correspond to the old in those areas where they're valid. Remember the bit about extrapolation. You can't extrapolate Newton's laws out to very, very tiny, tiny things. You have to change, and you come up with a better theory which works over the whole range. Okay, now the statistical interpretation of quantum mechanics. This is the biggie. The uncertainty principle puts a limit on our knowledge. No matter how carefully you do an experiment, there's always going to be a little error in your result. Okay? We can see by analogy that this applies to other kinds of research, because you can't really do an experiment on something without possibly changing it somewhat. This is one of the real biggies in, shall we say, psychology, because if you're going to do an experiment on somebody, you're going to change them a little bit. Is that ethical, depending on what you're doing? So the uncertainty principle can be generalized, although it doesn't involve Planck's constant in that case. The other thing has to do with the statistical interpretation of quantum mechanics. And this has to say, all right, I can come up with these mathematical formulas for matter waves, a wave associated with any particle you want to name. And that wave, just like the electromagnetic wave of light, doesn't tell me where the particle is or how fast it's going. It gives me a probability distribution, so that the probability that the particle is at a certain location is very high or low. And again, for those of you who like probabilities, statistics or something like that, we have you can draw curves, and they all tend to have this shape of a bell curve, something like that. And so you'd have one curve, and this would be, let's say, position, where you are, and the probability that you're going to find the particle at a particular time t at a particular location would be given by this curve. The probability that's here is the greatest, but it might be over here, it might be over here, it might be way out here, but the probability is very low. So it's a probabilistic interpretation of the waves to explain where the particles are. And the width of this has to do with the uncertainty you're going to have in your measurement. And this mathematically connects then to another probability curve, which is the probability of velocity or momentum that says at a given position, here's what your momentum probability distribution is, so that it could be anywhere in here, but you don't know exactly where. And the width of these two things together give you this uncertainty relationship. Well, statistics and statistical interpretation of quantum mechanics. Einstein didn't like it. He made the famous statement that he didn't think God played dice with the universe. But Einstein kind of lost out in the discussion to the other school of thought called the Copenhagen School, which had their interpretation of the statistical nature of reality in saying that there are many, many different ways that things can be, and you just don't know which one it is until you look, okay? But before you look, it's all of them. Well, that sort of, plays with your mind a little bit. And so there's this Schrodinger's cat. You've heard of Schrodinger's cat? This was an experiment, a thought experiment by Schrodinger to try to refute the Copenhagen interpretation. But let me just tell you this, it's interesting enough, I think, to spend a little time on. Schrodinger's cat, if you don't know about it, is this. You take a cat, okay, I'm not an artist, okay, here's a cat. Okay, here's a cat, and he's in a box. Also in the box is a vial of cyanide, very dangerous stuff, and another little thing of radioactive material. When this radioactive material emits a gamma ray in that direction, it will cause the cyanide vial to break, open up, and kill the cat. Now, when the radioactive decay occurs is statistical. There's a probability that the decay will occur in a certain length of time called the half-life. Heard of half-lives? So half of the material will be gone in a half-life. Well, anyhow, it's statistical. So as long as the box is closed, you don't know whether the cat's dead or alive. But if you open the box, you'll find out. Now, the Copenhagen interpretation was the cat is both dead and alive until you look. And that is obviously ridiculous, and that's what Schrodinger was trying to say. But it still is the orthodox understanding of quantum mechanics in that there's this statistical element to it. And that eliminates mechanistic determinism that we get out of Newtonian mechanics. Okay. Well, now comes the philosophical part, or the theology part. With this statistical uncertainty, God can act to affect outcomes without violating any laws of nature. All he has to do is select which one of these possible states is the true one. That take a while to think in. Okay. There's a paper called Statistical Freedom of the Will. And it's a way to reconcile the otherwise illogical conclusion of God's foreknowledge and human freedom and responsibility. Now, the paper itself is pretty long, and it's by a very famous person. He wouldn't be famous to you necessarily, but his name's Warren Weaver, and he was very much part of developing what's called information theory. And he gave this as an address, and it then got published. And it's about 4 or 5 pages long, and it's not saying anything about God in it. He's not being religious, but he is talking about statistical freedom versus trends which are foreseeable. That is, when you're dealing with a large group of people, for example, you would know something about their natures and you could predict what was going to happen with this group pretty well without necessarily predicting what each individual would do. And that's the idea behind this, that it's perfectly obvious that God can know the result of the future, of what's going to happen, without necessarily forcing an individual to be the causative agent in it. Okay, that's philosophy. It gets a little complicated there, but it's an interesting viewpoint to read. There's another paper similar to that one that is titled Reflections of a Communication Engineer, which was something slightly different, but it's dealing with statistics again. And in this case, this communications engineer was speaking to a group of people who weren't, which is why he gave that title to his talk. But he had some interesting observations in it, and some of them I have maybe heard in other contexts, but this one is quite interesting. And it had to do with spontaneous creation of life, because you've maybe heard of that as a possibility. And he said, well, there had been some work done on robots, saying, what would you have to get a self-producing robot, one that could go and pull the parts out of the bins and build itself, assuming the parts are all there in the bins and the robot had the ability to do that. How much information would a robot have to be able to do that? And his answer is it came out to be 1,500 bits of information. Now, what in the world is 1,500 bits of information? Well, it means 1,500 yes or no questions, okay? True or false kind of things. That's a binary. Binary is what the B is for in bit, BI, binary. So 1,500. And he said that was their conclusion on a robot, to be self-creating. Well, the interesting part of that was also about the amount of information that was in the smallest protein that could reassemble itself out of a nutrient batch, which was kind of interesting because that was like the smallest amount you'd have a self-duplicating protein molecule. So you got to get that one somehow to start off the system. So it's like probability 2 out of 2 to the 1,500 times. That is a very big number, by the way, in order to get the spontaneous creation of life. And the answer to that is it ain't going to happen. Okay. There's, on that basis, there's no point in looking for life on Mars if you think it had to arrive spontaneously. It causes me to say it might be worthwhile looking for life on Mars, because if you find it, that would be a tremendous proof of God's existence. Because you can make the argument that life arose spontaneously here. Okay, there's not that many stars in the universe. Okay, so you have to have multiple universes in order to get one that works, and we just happen to be in it. Okay, well, that's a nice theory, okay, but if so, we're unique. So then if you go out and you find on another planet some living things, whoa, the probability is just doubled that can't happen, because if it takes so many universes to get one starting alive, how are you going to get 2? That's why I'm saying if you ever hear that SETI, the search for intelligent life, ever succeeds, that's a tremendous proof for the existence of God. Personally, I don't think it's going to succeed. Okay, well, I haven't left much time for questions. Anybody have any questions out of all this? I realize if you've never studied this before, it's a lot to try to take in. But if you stop and ponder it a little bit, there are these basic core ideas. And that is, when you get to the very, very small, the intuitive feelings that we have about mechanics, which Newton put into mathematical terms, don't work anymore. The new explanations that do work and have been shown with experiment to be very accurate, these new explanations put this statistical bent on things, that there's this uncertainty principle which kind of pervades everything. You can't ever be perfect and know everything. And then there's the idea that things happen at random, which is kind of goes against the grain, that everything happens at random. But that's the philosophical underlying of it. But you have to understand that there's a higher power over this, so that things are not really random as they seem to us, that there's a purpose in it, and that hopefully that is giving us a little bit of encouragement in our faith. Now, this was one end of what happened at the beginning of the 20th century, looking at things that were small, photons of light, electrons moving around, atoms, and so on. The other end of it is things going very, very fast. And that's what led to the theory of relativity. And so next week, we're going to talk about the theory of relativity and the nature of time, which is very much connected into that. And I will tell you that this business of downloading class materials, if you want to do it, all you can get is copies of these slides plus the handout. There's not really anything else there right now. The important stuff, though, is maybe the whole text of all this that I gave originally to the seminary, which is probably more interesting to read than just these notes from these sessions. And then there is, I think I have put out there another interesting little hypothesis or theory that I worked out myself, and it's called Proof You Have a Soul. And I've shown that to a number of people, and I've never gotten any responses back, which causes me to wonder if it's just me, but I found it a very compelling thing. So if you want to look at that, it's out there too, where all the other things are. Proof You Have a Soul. Maybe you already knew that, but I was going to say to prove it to you. Okay. I'm being facetious here, okay? It's just very short, one page, less than a page. Okay, now, any questions? Hearing none, we will close with a prayer. Dear Lord, the world that you have made is very great, and you're letting us understand it a little bit at a time. We know that it's hard work sometimes to understand all that you have done, but we thank you for allowing us to do so. And we pray that the more we understand of your world, the more committed we are to you, knowing of your goodness, your mercy, and your care, and how you guide all that happens. We give you thanks and praise for all this in Jesus' name. Amen. Thank you all. I hope to see you next week.